Hello everyone, in this video I will discuss about Orgel diagram. Okay, Orgel diagram, this is part 2. So you have to know this one. Actually this one is what Orgel diagram. This is applicable for this what? Okay, for high spin or low spin, like this. Weak field or this one strong field, like this. Then configuration, some configuration I have to discuss, configuration and energy term also. Okay, energy term. Then spin multiplicity also, on which one is ground state, excited state, this one also I will discuss, and some rules also for Orgel diagram. Okay, after that this one is Orgel diagram and electronic spectra for D1. Okay, D1 and D9, like this. So now see Orgel diagram. Okay, this is Orgel diagram. This Orgel diagram, some this a statement needed. Statement is, see, Orgel diagram are used for the interpretation. Okay, interpretation of the spin allowed absorption bands of DD origin in the electronic spectra, electronic spectra. So here also electronic spectra, this electronic spectra for tetrahedral and octahedral transition metal complex. Okay, so electronic spectra of tetrahedral and octahedral metal complexes. Okay, so this one is Orgel diagram. This Orgel diagram are used for the interpretation of the spin allowed. The spin allowed and spin forbidden, you know this one. Okay, this one is spin allowed absorption bands of DD origin in the electronic spectra for tetrahedral and this one is octahedral metal complexes. So octahedral metal complexes, some example. Okay, see example, this one is titanium H2O whole 6 then 3 plus. This is a metal complex. Okay, this is a octahedral. So another one, spin allowed transition occurs. Now spin allowed, so spin allowed transitions occurs between the two energy levels. So two energy levels, maybe this one is two energy levels, maybe this T2G or EG. Okay, two energy levels. This one is ground state or excited state, like this. Understood? So two energy levels which have the same multiplicity. Two energy levels which have the same what? Same is spin multiplicity. Okay, multiplicity, spin multiplicity, that means this one 2s plus 1. Okay, 2s plus 1, this is spin multiplicity formula, 2s plus 1. Here s equal to what? S equal to spin, then s equal to spin, then s equal to this one is spin. So s formula, s equal to n into half. This n equal to number of unpaired electron, this n equal to number of unpaired electron. Okay, electron or electrons. Understood? This one. The spin multiplicity. Okay, same spin multiplicity, or sometimes delta S equal to 0. So delta S equal to 0 means spin multiplicity. Suppose a spin multiplicity is 5. Okay, so like this, T1G. Suppose this is hypothetically. Okay, 5 T1G. Now T2G like 5. So this one, this spin multiplicity are same. Okay, this one. Understood? So, okay, now this for excess state, and this one is excess state and ground state. So some configuration have to know. This configuration. Okay, configuration. Suppose D1, okay, and D9. So D1 and D9, this one is this energy term. This energy term is energy term. This energy term is what? Energy term is 2D. Okay, how this one came 2D? So now I have to explain this one. D1 term have to find out. Okay, term. Now D1. So you know this one's d orbital, 5d orbital is there. Okay, 5d orbitals, 1 2 3 4 5. So this one is dxy orbital, this one what, dyz, and this one dzx, and this one dx square minus y square and dz square. Okay, now this one is 1. How many electrons here? 1 electron to 1. Now what about magnetic quantum number? So magnetic quantum number nothing but here +2 +1 0 -1 -2, this one. Then L value is what? L value is +2 into 1 1. Okay, so here to this one, so empty. Okay, empty, that means 0. So 1 into 0, so 0 0 into 0, this one also 0 0 into this one in 0 0 into this one. So this one no need. So here this one 0, right? That means 0 into this 0 into 1, so 0 plus this 0 0 into here 0, no electrons, 0 into this -1, and 0 into -1, then 0, you can write 0, and 0 into this one, then 0 also. So this one is 0, only 2. Now 2. So now 2, this one's, if L value is 0, 1 2, if L value is 0, then you can write S. If L value is 1, you can write P. If L value is 2, then you can write D. Okay, now this one is state. This energy state is D. Okay, this D. Now what about the spin multiplicity? So spin multiplicity, this one is 2s plus 1. So here how many unpaired electrons? Only one unpaired electron. And spin formula, spin equal to n into 1 by 2. So n equal to what? 1 into 2, then half. Okay, half. This half have to put here 2 into the here. S value is now is half plus 1. You can cut, then 1 plus 1 equal to 2. That's why 2. Understood? This one. And this D9 also. Okay, this D9. So this D9 term symbols have to find out on D9. Like this have to do. Okay, 1 2 3 4 5. Then 1 2 3 4 5 6 7 8 9. Okay, 9. Now magnetic quantum number 2 plus 1 0 minus 1 minus 2. So L equal to how much? L equal to 2 into how many electrons here? There are 2 electrons, then 2 plus 1 into how many electrons? 2 plus 0 into 2 minus 1 into 2, and here minus 2 into 1, like this. Then this is 4, 2, here 0, here 2, here also 2. Then so this one can cancel, only 2 is remain. 2 means D. Okay, now whatever spin multiplicity, it is denoted by 2s plus 1. How many unpaired electrons? Only one unpaired electrons. If one unpaired electron, S value is what? 1 n by 2, then 1 by 2. Now 2 into 1 by 2 plus 1 equal to this one how much? 2. Understood? This is spin. Now this is term. Okay, spin multiplicity 2, then 2d. Understood? No, now you have to know this one. Here d9. This d9 can participate in that one whole formalism. Okay, whole formalism or whole transfer mechanism. Okay, so whole transfer mechanism or whole formalism means, see here how many electrons in d orbitals? 9, like this. 1 2 3 4 5 6 7 8 9. This whole formalism, this one can participate. Why this one can participate? Because see, here one electron less than from the this fulfilled configuration. Okay, मेरा मतलब है this one is see how many electrons less. So how many electrons less from fulfilled? 1 electron. Okay, 1 electron. That's why this one can participate whole formalism. That means this one is normal splitting. Here normal splitting is what? Normal splitting is like this. Like this. Suppose D, na? This one is term is D. Normal splitting like this one and this one is there. Okay, this side. This one is T2G. Okay. Sorry. Now this one T2G and EG, and here this side EG, and this side is what? T2G. Okay, this one for octahedral. Okay, in octahedral, this one for octahedral, and this configuration also. Suppose this is octahedral, this one is tetrahedral. In octahedral case, this is lower limit. Okay, this one is what? Lower limit. Well, sorry, not lower limit, this is lower energy level. Lower energy level. Okay, this one is lower energy level and this one is higher energy level. In case of tetrahedral, this one is lower energy level and this one is higher energy level. Understood? Now this question arises, this one is what? D9, this one is whole formalism. So this normal splitting is octahedral. Now this inverse one. So if whole formalism is occurs, then this one is inverse. Inverse means, suppose here this is actually octahedral, na? Octahedral T2G and EG. Now this is inverse one. So inverse one you can write here EG and here T2G. Okay, like this. Understood? Like this. So see this one d orbital. Okay, 1 2 3 4 5. Now like this. This is top side is what? And down side. This one is EG, here T2G. 1 2 3 4 5 6 7 8 9 10. Okay, sorry, here 9. So 1 2 3 4 5 6 7 8 9. Okay, 9. Now this if one electron go here, okay, here. Now down here is hole can form one hole. Okay, one hole. Now this transition occurs from EG to T2G. Okay, transition occurs from EG to T2G. Why EG to T2G? Because see, this is whole formalism or whole transfer mechanism. The whole transfer mechanism, whole formalism. If this one is 1 electron less from the full field or half field, or another one is if 2 electron less, that means if दो इलेक्ट्रॉन less हो full field or half field से, तो that time this D9 or D8, okay, like this D9 or D8, D9 can form D9, D8, this side D4 and D3. So these are can participate in this whole formalism. Understood? This one. So if whole formalism participate, this one is reverse one. Okay, then splitting is reverse. If this one is octahedral place like this, then splitting is reverse. Then you can write this now that time this. Now see, octahedral place is what? Octahedral place is, this one is ground state. Here ground state which one? This is lower energy level, which one? T2G. But in this case, D9 case, here ground state is EG and excited state, this one is T2G. Okay, T2G, understood this one. So this is D9. Okay, I will discuss this later one nicely. Okay, now see, now Orgel diagram are used. Now another statement, Orgel diagram are used for assigning electronic transitions in weak field. Okay, weak field. So this is weak field, very important. This Orgel diagram applicable for only weak field. That means high spin, understood? Weak field or high spin. So this Orgel diagram are used for assigning electronic transition in weak field or high spin transition metal octahedral complex. The transition metal octahedral complex and all tetrahedral complexes, understood? Octahedral complex and tetrahedral complexes. So this one is weak field or high spin transition. Okay, this one applicable for weak spin, high spin, understood? So the diagram is this one, Orgel diagram. The Orgel diagram cannot be used for low spin. Okay, for low spin or strong field, this Orgel diagram cannot participate. Why cannot participate? Okay, why cannot participate this one? Strong octahedral field, strong. Okay, why can participate this one? This is strong octahedral field is stronger. Okay, stronger than DD interelectronic DD interelectronic repulsion. Okay, so this one, this Orgel diagram cannot be used for low spin or strong field complexes. Why? Because this one strong octahedral field is stronger than DD interelectronic repulsion. Okay, interelectronic repulsion, understood this one? Okay, now this is criteria. The Orgel diagram is presented in following ways. Orgel diagram is presented in following ways. Okay, so following ways. First one is what? Write down the spin multiplicity of ground state and excited state. Okay, first one is spin multiplicity. So write down the spin multiplicity. Of ground state and excited state. Okay, ground state and excited state, free ion terms in the desired diagram. Okay, now this free ion terms means, suppose what? Suppose you can use this one, TiH2O whole 6 then 3 plus. Here free ion means what? Titanium. Okay, titanium, suppose titanium 3 plus. So this is free ion. So spin multiplicity of ground state and excited state free ion terms. Now this is free ion. Now terms means suppose this one is suppose, then T2G, okay, T2G2 or EG, here 2, here 2. So this is spin multiplicity, okay, spin multiplicity, and the 2 T2G and 2 EG, okay, this one. This is one number. Now two number is write down the same multiplicity for the term, okay, same multiplicity, okay, same multiplicity. So same multiplicity is, suppose this one T2G, here 2 to 2EG, okay, same. This here multiplicity same, otherwise this one is forbidden transition, okay, forbidden. So same multiplicity, here 2 then 2, suppose here 3 then here also 3, now should be here 3. If 4, here also 4 needed. So spin multiplicity should be same, okay, this one. 3 number, write down the subscript, okay, subscript G for all terms or for all terms energy levels in the metal ions, okay, in energy levels metal ions. So third number, G, this G, okay, this is terms, energy level terms, T2G, okay, and EG. So this one for is octahedral complex, okay. If tetrahedral, no need to write. If octahedral complex is there, then you should use this G, okay. Then this is point number 3 is what? Write down the subscript, this is subscript G to all term symbols energy levels if the metal ion is in weak octahedral field, okay. If this one weak, this one actually Orgel diagram is applicable only for octahedral, weak octahedral, that means high spin, okay. So this G, when you will use this G, that means this if octahedral complex, then you can use G, otherwise no need to use, that means G is not written in weak tetrahedral field. So G is octahedral field you can write, and G cannot write in tetrahedral field, okay. In tetrahedral field no need to write, understood? So this one. And next this one, point number 4. Suppose point number 4, show all possible transitions from ground state to different access state, all possible transition. Suppose all possible transitions, see, and now this one D term symbol, okay, here like this, T2 2 T2G to this one is 2EG, okay. This is very center. Now transition, how to transition like this, here to this T2G to E2G, this is transition. So how many transition here? Only one transition for this one D1. For D1 how many transition possible? Only one transition is possible, okay. And for this one is D9. So D9 is how many transition is possible? Same 2, okay. Now okay, D9 I will discuss later. Now this one. So show all possibles, this point number 4, show all possible transition from ground state to different excited state, understood? This one, okay. Now suppose one complex is there, okay, you can consider this one Ti to 6 then 3 plus, okay. This one, for this complex, what is the Orgel diagram? or Orgel diagram and electronic spectra. The Orgel diagram and electronic spectra. Orgel diagram or electronic spectra. So this is very important, this Orgel diagram. Okay, and this one is either this MSc or this one IIT JAM or GATE, or this one is last CSIR, chemical science CSIR net. Okay, this one. Suppose this one is this one, there is only one electron. Okay, one electron. So this is titanium 3 plus, titanium 3 plus. So titanium if 3 plus, then actually this is atomic number is 22 minus 3. So 22 minus 3 how much? Then 22 minus 3 19. Okay, that means D1. If D1 electrons 1 only, so D1 electron, this is D1 system, D1 electron, then term symbol is what? D1 term symbol is 2D. This is term symbols. Okay, this one is term symbols. So this one, therefore it has only one energy term, only one energy term. Okay, so in the ground state, single electrons occupy the lower T2G level. Now in ground state, this one D, this side energy. Okay, this one. So ground state, this one T2G and this one is EG. Okay, here spin multiplicity how much? 2, then 2 right. Okay, this one. So this is lower energy level, this part is lower energy level or ground state, and this one is excited state, ground state, and this one excited state. Lower energy level is higher energy level. So single electron occupy in lower energy level, that means this is T2G level. Okay, in T2G level, this is octahedral splitting, which has 3 degenerate energy level. Okay, like this, or you can write like this also, D, this one is this side EG. Okay, EG, and this one 3. Here how many degenerate? So 3 degenerate energy level, 3 degenerate, XY, YZ, then ZX. Okay, here 3 degenerate energy level. Degenerate means what? Degenerate, this degenerate. Okay, this degenerate means equal energy, equal energy or same energy. Okay, here same energy. So this one 3 degenerate energy level, to 1 2 3. Okay, 3 degenerate energy level, it is called T2G. Okay, now on absorption of radiation, the electron gets excited state. Okay, here 1 electron is there because D1 na, D1, so 1 electron here. So this electron can excited. Okay, in excited state will go like this. Okay, then excited T2G to EG. Then on absorption of, so you can write here, on absorption of radiation, the electron or electrons, so here 1 electron, then only electron, so electron gets excited to EG orbital. Okay, then T2G orbital to EG orbital, so electron gets excited to EG orbital, here to here. Okay, this one understood. The electron in the EG orbital. Okay, electron in the EG orbital, here EG orbitals. The EG orbitals have 2 degenerate orbitals. This EG orbitals have 2 degenerate. First one, this one and this one. So what is the name? This one. Okay, this first one name is dx square minus y square. And second one name, this second one, this one dz square, okay, dz square. Here two energy, two degenerate orbitals of equal energy, and it is called Eg, okay, this one. So consequently the absorption spectrum of D1, okay, in D1, okay, then this D1, see, absorption spectrum of D1 ions shows only one band, okay, shows only one band. So how to write only one band? Suppose this one is graph, okay, this side is E energy, this side E, and this side is frequency in centimeter inverse. So you can write here total, and suppose here 300, okay, 20,300. So 20,300 and this side, so one graph like this you can write, okay. So this one, okay, so this one is this 22,000 this side, okay, 22,300. Actually this one is titanium. You have to buy this one, okay. Titanium is 2, titanium is 2O whole 6, then 3 minus, okay, 3 minus, 3 minus, then 3 plus, sorry, 3 plus, 3 plus this one. So this 3 plus, this absorption band is 22,300 centimeter inverse, okay. This one is absorption band, and can be assigned, this one can be assigned, this one is T2G level to EG, okay, to EG level. Understood? This is transition. The transition can possible, this transition, okay. Here this one, the transition can possible, see, the 2T2G level to 2EG level. So one splitting, one transition is allowed, okay, this one. Understood? So the magnitude of this last conclusion is what? Conclusion is, see, the magnitude of the splitting depends on the nature of the ligands and affects the energy of transition, okay, transition, and hence the frequency of maximum absorption in the spectrum, okay. Then frequency of maximum absorption in the spectrum. Understood? So thus the peak occurs, suppose another one is 13,000, okay, 13,000 centimeter inverse. In 13,000 centimeter inverse, this one is titanium TiCl6, then 3 minus, okay, this one. And another one is in 18,900 centimeter inverse. So 18,900 centimeter inverse in this one is what? TiF6, okay, TiF6, this one also 3 minus. So understood? So all are, this one is F, this is weak ligand, this one also weak ligand. So overall is what? Overall is Orgel diagram are applicable only for weak field and weak ligand or weak field or high spin complexes, okay, this one. Understood? So in next video I will discuss another one. This one is this T2, D2, then D3, D4, like this, okay. So this video now is 34, okay, 34 minutes already gone. So this next video I will discuss this later. Okay, this one Orgel diagram 2 3 4. Okay, this part is there, so many part is there. Okay.